All right, so tonight we're going to look at 11.8 and first half of 11.9. We're going to basically look at power series and how to do some calculations and stuff with them. If you went to the website, you'll notice the notes there, the PDFs there, and there's also a video. Those are the videos I created last semester for my class when we were doing the virtual at that point. So it just gives you another little aspect or opportunity to look at. They're only like, I think for these, they're only like 5 or 6 minutes long. So if you just want to get a quick overview of them, to review, you can use those videos as well instead of listening through the whole lecture like we're going to do tonight. Um, so a power series is of the format of some constant times x or times x to the nth power. So the difference between the power series and what we've been looking at in the past is there's a variable built into it. So the variable x allows us to have a range of values that'll work. So we're going to have to figure out um, what they converge to and when they converge. So if they can, and it's going to be a range. So some values are going to converge from -1 to 1. Some are going to only converge above 0, things like that. So we have to figure out the interval of convergence, it's actually called when we're actually doing these out. So that's what we're going to look at. The key though is when we're looking at them is actually taking the problem and turning it into the correct format so we can actually come up with those problems, and doing the ratio test and those things to figure out where they actually converge and diverge. So if we look at the simple equation, just x to the n, so we're just doing the summation of x to the n. So we have 1 plus x squared plus x to all the way to the nth power. Now we know this one's going to converge when x is -1 to 1. And that's because, for all intents and purposes, this is a geometric series. And x is no different than my ratio for the geometric series. So I know on my geometric series, it converges when the absolute value of x is less than 1. And it diverges when the absolute value of x is either greater than 1 or equal to 1. So if we can get the problems looking like this, it makes our lives a little bit easier, or we have to do the ratio test. So that's basically what the power series is going to be looking at, is what's the values of x that's going to converge and diverge. So we look at this, a couple examples. That's the 1/2 one, that's the 2 one, and we can see this converges and this diverges. We also can put in a value there. So x minus a, some other value, and that a is going to be a constant. This one is a power series centered around a certain point. So we can have it centered around 3 or 5, or whatever the value happens to be. When we're looking at those, it's going to change my method of convergence too, because now it's x minus a has to equal 1 instead of just x. So that's going to change my when it's going to converge and diverge. I'll look at a couple of those in a second though. So, all right, let's look at a couple examples and see how this actually works and how we actually use this. So we want to figure out which values of x the series convergence. So we have n factorial times x to the n power. So we still have to go back and use the test that we had before. Now this one's got the factorial built into it and a power. So one of the tests that works really well for that is the ratio test, because we have a factorial in there. Let's look at the ratio test. So we have a sub n plus 1 over a to the n. So I have n plus 1 factorial times x to the n plus 1, and then n factorial, and then x to the n on the bottom. So when we simplify this out, if we look at that n plus 1 factorial, remember changes to n plus 1 times n factorial. So we can cancel out the two n factorials. And x to the n plus 1 is the same thing as saying x to the n times x. So we can cancel out the two x to the n's. And what we're left with is x plus 1 times the absolute value of x. Or n plus 1, sorry. Now for this one, as that n goes to infinity, this whole function is going to infinity. So by the ratio test, this series is going to basically diverge everywhere except where x is 0. So the only time it's going to converge would be x equals 0, because 0 times anything is going to be 0. So it would converge to 0 at that point. So this one diverges when x is everything except for 0. So it only converges when x is 0. Does that make sense, how they went through and did that one, and why it converges at that point?
Yeah, that makes sense.
All right. Let's look at another example. All right, so we've got this one. So we want to figure out where this one converges. So we're going to do the exact same thing. We're going to do our ratio test. So my a to the n, or my a sub n, is going to be x minus 3 to the nth over n. So we'll set up our ratio test. We have x minus 3 to the n plus 1 over n plus 1 times, and then we flip the second one, x minus 3 to the n. So if I clean this up a little bit, I'm going to have n over n plus 1 times x minus 3. Because it basically canceled out the x to the n, and I'm left with that plus 1, which is the x minus 3 to the first power. Now I'm looking at the limit of that, so it's looking at the limit as n goes to infinity of n over n plus 1 times x minus 3. So that first part, we can divide everything by n. So I have 1 over 1 plus 1 over n times x minus 3. So this first part goes to 1. So this function, as the limit goes, as x goes to infinity, goes to x minus 3, the absolute value of x minus 3. Does that part make sense?
Yeah.
Okay. Now, the next piece we have to do on this so we now know that since it's a ratio test, I know the ratio test converges when it's less than 1, because that's when they converge, and it diverges when it's greater than 1. So let's actually solve this one out, figure out where it converges and diverges. So we have x minus 3 is less than -1 or greater than -1 to 1. So I add 3 to all the sides. So I've got 2 is less than x is less than 4. So I know it converges between 2 and 4, but we're not done yet. We have to look at what happens at 2 and what happens at 4. Because remember, the ratio test, if it equals 1, we don't know what's going on. So we just know what happens when it's less than 1 or when it's greater than 1. When it equals 1, it could be both divergent and convergent, or convergent. So we have to figure that piece out. So we basically have to go back and look at our problem and plug in those numbers and see what kind of function we have to determine if it's convergent at that one or divergent at that one. What's up? Okay, I didn't know if I had a question. So let's look at the 2. So I have, if I plug in 2, I get this. So,
what you're writing now isn't showing.
Oh, thank you. Because I forgot to switch there. Okay, so there was what I was just talking about. The x minus 3 is less than 1. And I got down to 2 less than x less than 4. Just tell me, I'm working on 2 computers, and sometimes I forget to switch the one that actually is sending to you. All right, so I'm going to plug in the 2 and I'm going to plug in the 4 to the x and see what happens at each of those. So if I plug in 2, I get the summation of -1 to the n over n. Now, that series right there, if I plug in 2, that's the alternating harmonic series, correct? And the alternating harmonic series, does that converge or diverge?
Diverge.
Nope, the alternating one converges. The regular harmonic series does not. So if we look at this one, that passes the alternating series test because its limit is 0, it's decreasing. So therefore it passes the alternating series test. So 2 converges because of the alternating series test. So I'm going to put a little less or equal to symbol underneath the 2, the less than there, or the greater than. So it's 2 is less than or equal to x now because the 2 will actually work. Now I also have to try the 4. So if I do 4 minus 3 to the n over n, that goes to the summation of 1 over n. Now 1 over n, that right there is the harmonic series, and the harmonic series diverges. So I'm not going to change the 4. So this series converges when 2 is less than or equal to x, which is less than 4. That part makes sense? Actually, I want to do another one of those for you guys. Let's find one real quick. Let's do, yeah, let's do that one. All right. So when we're doing these, the first thing we want to do is we're going to do the ratio test with it to determine when they're going to converge and diverge, the basic format of it. So step 1, ratio test. So I'm going to do x to the n plus 1 over 2n plus 1 minus 1. And then I flip it. So it's 2 minus 1 over x to the n. So this becomes 2n plus 1. All right. So if I simplify this down, I get the limit as n goes to infinity of 2n minus 1 over 2n plus 1, and then times the absolute value of x. Does that part make sense?
Yeah.
Yeah.
All right. So now we're going to do the limit of this one. So I'm going to divide everything by divide them all by the ends so I can get the ends in the bottom so I can figure out what it's going to go to. So this goes to 2 minus 1 over n over 2 plus 1 over n. So this ends up going to 1. So basically it just goes to the absolute value of x. That part makes sense?
Yep.
Okay. So now that we know that part, so now the ratio test converges when it's less than 1. So I want to look at the absolute value of x is less than 1. So that means -1 to x to 1. So what I have to do next, I have to test the -1 and the 1. So if we plug them into this problem, so I have -1 to the nth power over 2n minus 1. So now, does that converge or diverge? So this is an alternating series because -1 is up on top. So the alternating series test says the limit has to go to 0 and it has to be decreasing. This I know is decreasing. Now the question is, does the limit go to 0? So I have 1 over 2n minus 1. Does that go to 0? Yeah. So this converges because of the alternating series test. So I add the equal to symbol for that -1. That part makes sense?
Yeah.
All right, so next thing we have to do is we have to do the we have to do the positive 1, 1. So if I plug in 1, I get 1 over 2n minus 1. So now this one, I don't have anything that is the 2n minus 1 on the bottom. But if I look at that, I can look at the 1 minus 2n minus 1. That's greater than 1 over 2n. And that's the same thing as saying 1 over 2 times 1 over n. Now 1 over n is my harmonic series, correct? So I know that diverges. So since that diverges and my original function was bigger than that, because of comparison, that diverges. So I'm not going to add the equal to sign for there. So my answer is -1 less than or equal to x less than 1. Or if you write it as an interval, it would be -1 to 1 with the parentheses like that. So those are the two different ways you could write the answer. Does that make sense now? Before we go on to the next piece.
Yes.
All right. Thank you for answering. All right. The basal functions one, I'm just going to briefly go over it. It's basically of this format. So it's one of the uses that come up in physics and chemistry quite often. So we're not going to go through and solve out the basal function, but basically it says it's this power series that converges down to that shape. All right. The theorem for the power series. This is a more important piece. So any given power series, there's only 3 possibilities. The series converges only when the value x equals a, which now, if you look at this one right here, if x equals a, what does that parenthesis equal?
Zero.
Right. So that's one option, is only basically when the parenthesis equals 0. And that was the case when we looked at example number 1, was it only occurs when x is 0. The series converges for all x's, so no matter what the x value is, it's going to converge. Or there's a positive value r that it can converge around. That r is known as the radius of convergence. So if we look back here, my radius of convergence in this one was 1, because it's going from -1 to 1. My radius of convergence in this one was 1 as well, because it's going to, notice how it's going to converge. The radius is 1. It doesn't mean the values at the end are 1. It just means that from the center out is 1 space. So if you notice, like, just think about it in like a circle. The radius is 1, my diameter is 2. So from 2 to 4 is 2 spaces. And then it diverges the other direction. So the interval of convergence, we can write a couple different ways. The same thing. Case 1, it's just a single point. Case 2 is negative infinity to infinity. And case 3 is the inequality that we write. So here's a few examples that we looked or that we saw. The geometric series. That was the x to the nth power. Its radius of convergence is 1, and its interval converges from -1 to 1. And that we know from what we did before with the geometric series. The first example we looked at, the radius of convergence was 0. There was no change in it, and the only value that works is 0. Example 2 that we looked at, the radius of convergence is still 1, just what I just showed you, and we're going from 2 to 4. And notice how they put it with the 2 with the bracket and the 4 with the parenthesis. The basal function, which I really didn't talk about much, its radius of convergence is infinity, so basically converges for any value of x. So no matter what the value of x is, this will converge. All right. Let's do another one, a little more complicated one. So the first thing I want you to do for this one is take it and find me where it's going to, like, do the limit part, the ratio test, and find me the final part of the ratio test. So in essence, I want you to find this piece. So do the limit part and get down to that part there. And then we'll do the next step.
think you're muted.
And I am.
Okay.
God, it just isn't my day today. Not switching things, not unmuting myself. All right. Is there any questions on where I got the three absolute value of x? All right. So with the ratio test, that means 3 absolute value of x has to be less than 1. So that means the absolute value of x has to be less than 1/3. So my radius, so this right here, that's my radius of convergence. And that's my interval. So now we have to figure out if it works at negative 1/3 and positive 1/3. So we're going to look at these two series. And you have to determine if they converge or diverge at each of those points. So do your tests and determine if they converge or each of those points either or series converge or diverge. So when you're looking at these, it's nicer to simplify them down a little bit. So the top ends up becoming just 1, and this is just n plus 1. And this one becomes negative 1 to the nth power n plus 1 when you simplify them down. So that first series, does it converge or diverge, and why?
It, let me see. Is it inconclusive because it's equal to 1?
So you're not going to do the, so you're right. If you did the ratio test in this one, you're going to get it's inconclusive. So you can't do the ratio test to determine if this part is convergent or divergent. So if you do a test and it comes out to be inconclusive, you have to try another test. So you have to always come up with the reason either it's convergent or divergent. For this one, the best way to do it is actually to notice it's really no different than the power series. It's this one right here is very close to being just 1 over the square root of n. And I know 1 over the square root of n diverges because the p is 1/2. So this part here, this one right there, diverges. The second one, we could use what test for? What's the test we want to use whenever there's a negative 1 in it?
Alternating series.
Yeah, let's try the alternating series test. And this one, it passes the alternating series test. So this one converges based on the alternating series test. So I'm going to put the little line under there. So that means my interval is going to be negative 1/3 to 1/3. And that would be the answer. So the power series is a really good test because you have to go back and actually use all the rest of the tests to still do those series. So it's not like just like, oh, we're done. We did the ratio test. We're done. We actually have to go back and use some other tests to figure out if the endpoints converge or diverge. All right, let's look at one more of these. All right. Work this one down to get the limit part first. And then check that, and then we can do the radius of convergence and the interval of convergence. All right, so this limit should break down to the absolute value of x plus 2 over 3 when we do this one. Everybody get to that?
How did you get n at the bottom of the n plus 1?
So the x plus 2 basically end up canceling out. So this x plus 2 to the n cancels out that part basically. So I'm left with this n right down there.
Oh, okay.
And I can't cancel it out with the n plus 1 because it's not n times 1. Although the thing about this one is when you actually do this limit out, when you divide them all, you end up getting 1 plus 1 over n over 1, which still comes out to be 1 anyway. So if for some reason you messed it up and actually got rid of the n in there, you're still going to end up with 1.
And then, oh no, I see. I was going to ask where the 3 went, but I see there's a 3 still there. Okay.
Yep, the 3 still on the bottom because I had the 3 to the ends end up canceling each other out, but I have 3 on top and 3 squared on the bottom. So that's where the 3 is left in the bottom. So now,
It's
yep, go
not
ahead.
3 squared.
No, because I have, so this one up here, I end up with 3 there, and down here I end up with 3 squared. So that 3 cancels out the 1 extra, the 3's in the bottom.
Okay.
So now I'm setting x plus 2 over 3 has to be less than 1. So I have x plus 2 is less than 3. So that right there is my radius of conversion. And then my interval is going to be from -5 to 1. And that's my interval. So the next thing we have to do is we have to figure out, we have to plug the -5 and the 1 in to see which is going to work. So my first one, I have n. If I plug the -5 in, I get -3 to the nth power over 3n plus 1. And the other one, if I plug in the 1, I get n3 to the nth power over 3n plus 1. So this series, this simple kind of works down to -1 to the n times n over 3. And this one just works down to n over 3. So that first series, what are we going to use to test it?
Alternating series test.
All right, so if you do the alternating series test, the limit has to be 0 and it has to be decreasing, or has to be going in the same direction. So this one, and the limit is n goes to infinity, is going to infinity, so it is not equal to 0. So it fails the alternating series test. So now remember, failing the alternating series test does not tell me that it diverges. It just tells me that it fails that test.
So then we would just do the divergence test, right?
Yep. So you just do the divergence test. In this case, since my limit does not equal 0, it doesn't converge to 0, it diverges. So this one diverges. And actually this one, the second one, you're going to do the exact same test on. So this one also diverges. So my answer is -5 to 1 for this one. All right.
The bottom one diverges just because it goes to infinity.
Yep. And the same thing with the top one. The top one goes to infinity too. So it just goes to infinity and negative infinity because it's going to keep bouncing back and forth. All right. All right, let's look at 11.9 a little bit. So 11.9 wants us to be able to take a function and represent it as a power series. So one of the things that we've noticed is that 1 over 1 minus x. So if I took 1 plus x squared plus x to the third and so on and forth, that sum, it converges to 1 over 1 minus x. If it converges. So remember as long as x is less than or equal to 1, the absolute value of it, or less than 1, this is going to converge to that point. Because that's just our geometric series. And we looked at the beginning, that was what the geometric series converges to. So if I can take a function and represent it like this, I can then come up with the series that is also going to give me that same value. So if my function's f of x is 1 over 1 minus x, I can actually say that function is also the same thing as saying the sum of n0 to infinity of x to the n. So those would be the exact same thing. So we want to be able to take a function and convert it into a power series. So you can start seeing some of the partial sums that works out there. All right, so let's look at what they mean by that, because the 1 over 1 minus x is simple. The problem is not every function is going to be 1 over 1 minus x. So if I've got the function 1 over 1 plus x squared, I want to be able to try to figure out how I can convert this into a power series. So the first thing we have to do is I have to take that and I have to convert it to my 1 over 1 minus x. So it's simple to change the plus to a minus. I just move it in there. So I have 1 over 1 minus negative x squared. So that value right there, that's my x. So does everybody see how they went from 1 over 1 plus x to 1 over 1 minus negative x squared? Stop clicking mouse. So that conversion was to get it to become the 1 over 1 minus x, to stay in that same format. And since it's in that format now, x is negative x squared. So I can replace in my summation, or my power series, I can replace the x with negative x squared. So that series right there is the representation of that function. Does that make sense or no?
Yeah, that makes sense.
Okay. Once we have it as a power series, we then can determine where it converges and diverges. Since it's a geometric series, we know it converges when whatever the x is less than 1. So I know negative x squared has to be less than 1. That means x squared has to be less than 1. And that means the absolute value of x has to be less than 1. So everybody understand how they basically just got rid of the absolute value sides because of the negative sign, and they did the square root of both sides, which gives you the plus or minus x, which puts the absolute value sign back into place. So my interval of convergence is from -1 to 1. Okay. And since it's a geometric series and we looked at it that way, I know it's not going to work at -1 or 1, because in a geometric series, it is always less than 1. When I did the ratio test, I had to actually test both of those because 1 is inconclusive. But in a geometric series, 1 is not inconclusive, so we do not have to test those values. So that would be my interval of convergence, and my radius is just 1.
So if you were writing it out, it would be like -1 is less than or equal to x, and then x is greater than or equal to 1.
Nope.
It would be
It's x. It's -1 is less than x is less than 1.
Okay,
And it's only less than, not equal to.
okay,
Because we don't have the equal sign in the problem here. That's why it's not equal to when we write it out. And those parentheses represent less than or equal greater than. If it was a bracket, it would have been the equal to symbol.
oh, okay.
All right. All right, let's do a few examples out. All right, so I've got 1 over x plus 2. Remember, my goal is to get it to be like that, 1 over 1 minus x. And then the absolute value of x has to be less than 1. So that's the pieces of information I'm going to use to do this. So I need to get 1 over x plus 2 to look like 1 over 1 minus x. So in this one, the first thing I'm going to do is I need to get the number in front, and I need to get the 1. So I'm going to take out the 2, and I'm going to change this to 1 plus x over 2. Does that part make sense?
Yeah, you just divided everything by 2.
Now I need to get it to be a minus in there. So I'm going to take this, change this to 1 over 2, 1 minus negative x over 2.
We don't have to do it to the numerator when we do this?
What, when I pulled out the 2 over here?
Yes.
No, because I'm not multiplying the numerator. I didn't take the 2 and put it out in the whole front. I just put it in the front of the bottom.
Okay.
So, and this, all I did is I just took out the negative sign basically. So those 2 negatives become the positive, or it was the positive. So that didn't change anything up on top either. So if I look at this, I can rewrite this as 1/2 times 1 over 1 minus negative x over 2. So my power series will have the 1/2 out in front. And then that's by x value. So it's negative x over 2 to the nth power. Does that part make sense?
Yeah.
All right. So you can rewrite this a little bit if you want. We don't not have to. They actually rewrite it in the book as -1 to the nth over 2n plus 1, and then times x to the n power. They rewrite it that way because they basically brought the 2 back in. So that's that 2, and the 2 to the nth power is there. And they would the negative sign to the negative first power, or -1 to the nth power there. You can leave it like this though. That's fine. Totally works. So now the next, go ahead.
When you're testing your equation, do you need to put that 1/2 back in, or can you just use the negative x over 2?
You can just use the negative x over 2. Because remember, a constant times a limit is just whatever the limit is times a constant. So you can pull out that constant. You don't have to worry about it inside of it.
Okay.
So now, so I've got this -1 x over 2. The absolute value of that has to be less than 1. So that becomes the absolute value of x has to be less than 2. So that means that's my radius, and my interval of convergence is -2 to 2. And again, since I did it as a geometric series, I don't have to test the -2 and 2. I know it only works between those values. And if I was to write this out with the inequality symbols, it would look like that.
You said because it's a geometric series, you don't have to test them?
Correct. Yep. Because I used the geometric test to create the function. So since it's a geometric series, I know it's always less than 1. I know it doesn't converge at 1. So when we were doing the other ones, the ratio test, I didn't know what happens at 1. That's why I had to test those values to figure out what happens, to see if it was either going to be convergent or divergent, and use a different test. All right. Let's do another one. So actually, we're going to do maybe 2 more problems of this. I'm not going to do that one. Let's do this one. All right, so convert that one to the 1/1 minus x. All right. You should, when you're breaking down the 4 over 2x plus 3. So now this is the first one that we had a number up on top. Notice how I basically ignored it and just pulled it out as a fraction out in front. The bottom, you swap around the 3's and you divide by 3 to get the 1 plus inside, and then just change that sign. So I pulled out the 4/3 in front, and then I have 1/1 minus -2/3 x. So then my power series is 4/3 times the summation of n goes from 0 to infinity of -2x over 3 to the nth power. All right, so any questions up to that point?
No.
Okay, so then we just got to come up with our, so I know this is going to converge from negative 2x over 3 is less than 1. So that means the absolute value of x is less than 3 over 2. So my interval is negative 3 over 2 to 3 over 2. So that's my radius, and that's my interval. All right, let's do another one. All right, we're gonna do 2 more. I'm gonna do this one and 1 more after this one. All right, so work on converting this one down to the 1 over 1 minus x. All right, so if we look at this one, look at how I dealt with the x squared. So the question is why can I do that with the x squared? I did it with the 4 in the previous problem and 2/3 and everything else, but why can I do it with the x squared?
Is it because it's less x to the 4th?
Nope. What's my summation? What's the value? What's the letter that's changing in my summation? So in my summation, I'm doing n equals 0 to infinity, right? So the n is changing, not the x. So in essence, in this problem, x is a constant, and I can pull constants out. Yeah, go ahead.
Okay. So x is a constant in this situation. Because-
Yes.
So we don't need to have it doesn't need to be negative x squared on the top.
Nope.
Alright.
So we can just pull out that x squared. The reason why I can't pull out the x inside the problem over here, like this x, is because that's raised to the 4n power. So that's being changed by the summation. So that's why that has to stay in there. But that x squared, there's no ends on it at all, so I can easily pull it out because I'm going to plug values in for x, and that's why it's a power series. So I can plug any value I want in for x. And since that's going to be a constant out in front, it doesn't really matter what it is. It's not going to change based on the ends.
How did you get the x on top if you took the x squared on top away?
This x here,
Yeah.
it's the x to the 4th over 16.
Oh, okay, never mind.
That's so basically the piece inside here is this value, this part right down here. That's this piece right here. That's still the same part. That's still that.
Oh yeah, I get it now.
So, all right. So I got to do the same thing. I still have to figure out my interval for this one. So I have the absolute value of negative x over 2 to the 4th power has to be less than 1, which is the same thing as saying the absolute value of x over 2 has to be less than 1. So that means the absolute value of x has to be less than 2. So my interval is negative 2 to 2. So that's my radius, and that's my interval.
How did you get rid of the x to the 4th?
I did the 4th root of 1,
Oh, okay.
which is still 1. So one nice thing about always using 1 in these problems is that roots and stuff like that all cancel each other out. All right, one more. All right. Remember, my goal is to get this to be something with 1 over 1 minus x. I need this to look like that. So as you probably have already figured out, the hardest part of this problem is converting the beginning part. The trick to this one, and I'll tell you before I switch over to mine, is somehow you have to get the top to look like x plus 2. All right. So there's, look over what I did and ask questions where you're lost. I somehow needed to get rid of that addition on the top,
So
or
we,
the subtraction on the top.
so you use -3 to get rid of it.
Yes. So basically, I took the -1 and I changed it to +2 -3, which is still -1. So I haven't changed the problem. But what that did is it then gave me x plus 2 on the top and on the bottom, which allowed me basically to get rid of my x on the top. So this part over here is really, I took that, split that up into the two fractions. So I have x plus 2 over x plus 2 minus 3 over x plus 2. So that allowed me to get rid of the x on the top. Or actually, I didn't really need to get rid of the x. I needed to get rid of the subtraction on the top. And then you work out the 3 over x plus 2 the same way that we did the other ones.
Why can you move the 1 out front when it's not multiplied?
Remember, one of the things in series, you can subtract everything by a series. You can actually split up series with a subtraction. So in essence, it's the series of n goes to 0 to infinity of 1, which is just 1. So that's how I can pull that out, because constants can
Okay.
come out in front. So now that we got it down to that part, we're just doing negative x over 2 is less than 1. So the absolute value of x has to be less than 2. So that's my radius. And my interval is -2 to 2.